Hello, everyone, and thank you for coming to today's Hi5 seminar. Today we have a speaker, Hunter Finney, a former undergraduate student who used to work in my lab at University of Mississippi, but has been accepted to a graduate program at the University of Utah. And he's going to be talking to you a little bit about some of his work, looking at size perception and illusions of that sort in virtual environments. So, without any further delay, Hunter, I'm going to turn this over to you.
All right. Thank you, Adam. So
University of Mississippi, but
this
has
is
been
gonna be my
accepted to a
talk
graduate
on
program.
the Ebbinghaus Illusion and how the history of it and further work that I've done, and hopefully inspire some of you to take on VR and show what you can do with it. But before we really get started, I'm gonna go ahead, and this is for all the people in the future. So if you have to take a break and come back, or something comes up, I'm gonna have all these slides numbered by topic. So if you need to take a break, you can come back during a transitional slide and not feel like you missed anything. Or if you feel lost, you can always check in the top left corner and see where we really are in this entire presentation. So anyway, this is me. So thanks to Dr. Jones for that great introduction. That's that's me, a more handsome version of me with my partner in crime next to me. As he mentioned, in my undergrad, I graduated in computer science from University of Mississippi. Spent most of my time at the Hi5 lab there, working in virtual environments. Uh, Now I'm a graduate student over at the University of Utah at the Visual Perception and Spatial Cognition Lab, which is currently run by Janine Stefanucci and Sarah Krim Regier. So to start us all off, we could get a little backstory on what's going on. Let's talk about this two-stream hypothesis for vision. There's another one for hearing that's also quite interesting if you want to check that out. But for vision, there's two streams. There's a dorsal and a ventral. So dorsal, think about a shark, a dorsal fin. That's on the top. And the ventral, well, that's the other side. That's the bottom. The dorsal controls action, usually referred to as the where stream. It works for visually guided actions like picking things up or anything in your close proximity. It's really susceptible to motion and high temporal actions. Responds pretty fast. The ventral is often referred to as the what stream, where it's object recognition and it pays really close attention to detail. It's relatively slower than the dorsal, but they both are pretty fast. So I'm gonna give you guys a quick, rundown, quick test. So you're one, you're looking out, you're really thirsty. It's a hot Mississippi day, and you sit out in the horizon as a crisp Dr. Pepper. You can just see the detail, the cold condensation coming off of it. That's using your ventral stream, recognizing that that's a Dr. Pepper and it's something that you want. So what you're going to do, you're going to reach out for it and grab it. And that is using your dorsal stream. That's you're visually guiding your hand to grab this Dr. Pepper so you can have a cool, refreshing drink. But that's all cool and all, but it's still a hypothesis. And how do we show that? How are we going to show what's going on? How do we prove it? How do we test it? So you can't really crack open the brain and put a ruler in it to measure things. The best ways to test. And that's where we enter the Ebbinghaus Illusion or Titchener circles. Both of these terms came about the same time. They both refer to the same illusion. So my first experience was to the Ebbinghaus Illusion, so I'll be referring to it as that for the rest of this talk. When you're looking at this, you might have been pre-exposed to this before, but that's actually a good thing. It proves my point even more. So there's these two circles. These orange circles in the middle are actually the same size, even though they look different. The one on the left looks considerably smaller, about 10% smaller than the one on the right. It's about 5% smaller than the original circle itself. And same thing for the right side looks larger than it actually is. Even if you know that this is going on, it still fools you. And that's really important, because no matter what, that's going to fool the what. It's going to fool your recognition of it, even though you already know what's happening. But so now we have this where it's almost universal that this is happening. And now we need to test, well, how can we test the where? How can we test action of this? Well, that's where this neat thing called grass aperture comes in. So it actually correlates pretty well as you're visually guiding to grab that Dr. Pepper. You don't really miss it all that often, or ever. Your grass never just knocks it over, or you just like you try and grab a 2-liter bottle, but really it's a Dr. Pepper. It's pretty accurate every time. And so scientists took this idea and put motion capture software on or hardware on people's fingers and had them go pick up discs. And so even when they report that there's a size difference, you're able to test whether or not their action is going to pick up on that size difference. So let's take a second and kind of like look at what's going on in these figures though. So you can see that on the top figure that this is pretty much a sheet of paper, and there's these figures of the Ebbinghaus Illusion laid on top of it. And a man's sitting up straight most likely, and reaching to pick up this disc. And then in this bottom figure, you can see that they changed it from a horizontal plane to more closer to a vertical plane. Still kind of slanted a little bit, but still it's up off the ground. And you can see that's probably held on by magnets. You can see that right over here is that it's a little thick, and it's probably held on by magnets. And so, and the same sort of thing happens. They're tracking the fingertips, and they're going to go grab it. So let's use your cynical brain for a second. What could we do? What's going on in both of those? That could be better. Are we measuring the right stuff? What's going on? And I give you just a second to ponder it. And now let's go over some things that's going on that could be different. We might not be measuring what we really, really want to. Does the vision of your hand matter? Are you changing your grasp as you get closer, or does it matter if your hand's being shown? Like, what if you closed your eyes while you did it? What if somehow you didn't see your hand? Does that change anything? What happens if you black out the stimulus and you just see your hand and you grab where you believe the stimulus is? And even this is in the real world, so we're bounded by real world attributes such as dimensions, shadow, lighting. So even a piece of paper is going to give off these 3D cues. Well, what about, we've only seen these illusions on flat pieces of paper where they're all the same dimension. Are 3D cues important? Are they not important? What if we looked at it with only one eye, took away a stereoscopic view, or motion parallax, things like that? Does the angle that you're looking at this matter? So you see the person in front is looking at this at a slight angle looking down, so the vision, the illusion's kind of distorted a little bit. So, I mean, obviously in the second picture, they tried to remedy that in a way. So there's a lot of things going on that the physical world really bounds us by. And trust me, these are really smart people doing these. These are incredible people doing these studies. So being nitpicky it kind of comes with the job. And this is a great figure that was published by Friends in 2001, where it shows a lot of these studies and how they've been, how all these different ways have been shown, like the vision of your hand or not vision of your hand, and things like that are all shown here in his in this graph. Definitely, if you're interested in this, definitely pause the video and check this out. I'm not going to go into all of it. Only some of it revolves around the Ebbinghaus illusion, but there's different illusions going on that he checks out. really cool stuff. But really, does any of this even matter if we're not measuring the right thing? Like, is this grasp really measuring what we want to measure? And some sort of people came around and was like, well, is this like a motor illusion or a perception illusion? Because what if when you're going in to grab and it's showing that you're, you know, the this traditional small up here, if that traditional small is supposed to look bigger and it looks bigger on your grasp, is it actually just being bigger because you're grabbing at the entire thing? And it's actually more obstacle avoidance than it is anything else. And that's a kind of a big deal. And so instead of really changing the what's going on, changing how our experiment procedure works, they've decided to change the illusion a little bit. They're going to adjust the gap between the main circle and the flanking circles to be equivalent in both cases. And that showed kind of interesting results in that it might be a motor illusion actually showing up in all these past experiments. So, now that we're changing the actual illusion, how much is that taking away? How much can that show? And a lot of studies actually took this adjusted small and kind of rolled with it to show a lot more evidence for and against. And if you harken back to that figure I showed you from Franz, a lot of people don't agree on whether or not the Ebbinghaus illusion is definite proof for the two-stream hypothesis. So it's caused a lot of stir in the community. And this illusion, the Ebbinghaus illusion, is actually a compound illusion. This is the Delboeuf illusion. It's seen a lot in like food illusions and like things that help you with diets. So, for example, this DiGiorno up here gives you a good idea of if you have a bigger plate, it's actually it makes you want to put more food on it because it looks like smaller amount of food, and the inverse happens when you have a smaller plate. And so you can this illusion isn't as strong as the Ebbinghaus, at least for me personally. And this illusion is actually subtracted from the Ebbinghaus illusion. And so now we're moving further and further away from the stimulus that really like made this illusion so strong. So if we're having problems with the real world measuring this and using our actions to measure this, and then we need to change the stimulus, well, that's when VR comes in. So VR is an amazing tool. It's wonderful. You're able to do things and collaborate with people to think laterally about problems rather than be held to the confines of real world geometry and physics. In VR, you can just say, shadows don't matter. Lights and lighting doesn't matter. Whether or not you phase through objects, you get any feedback or not, we can turn that off. And the real world, you're bound by Euclidean geometry, and it gets in the way a lot when you want to do something as specific as this. And so we're going to get into what our experiment was. And so to do that, we're going to establish a baseline of how our participants view these illusions. So this experiment, we did this on a flat screen monitor. Everyone was set approximately the same distance from the monitor, and they would take their user circle and try and match the size of our circle we present them. And that will give us a good estimation of how strong the illusion is for our participant pool. So we use analysis of variance to find out that these are indeed very strongly significantly different, and that the ones with a large flanker size, which is shown here underneath matching circle, is gives a participant's my bad. So the one that's shown in the matching circle is small flankers. So that gives you a perceived size difference of about 5.81% larger than what it actually is. If you were to have the larger flankers making the inner circle appear smaller, is a 4.04% decrease in size. So that establishes our groundwork on how our participants perceive this. So we take this into VR, and what's really neat about this, it addresses a lot of these older experiments and a lot of the problems, and removes a good chunk of them, even though it adds on other problems that we'll get to later from VR in general. So in VR, we have in this plain room. It's actually the current Hi5 lab right now, where it's a much more simplified, just walls and some tables. And then we have this illusion suspended in midair. It's 2D, and there's no shadows cast on it, and it's casting no shadows. What's interesting about it compared to the other ones is that each one of these illusions are pretty unique to the participant. And like, well, that doesn't sound very controlled and scientific at all. But really, what's controlled about it is that it looks pretty similar to each individual person by changing the distance compared to their arm's reach. So before they really get into this experiment, they would stick their arm out and pull the trigger on the Vive wand, the gamepad for a VR headset. And this measures how far their arm can reach, so we don't put anything out of reach or too close to them. And it also marks of where their head is. So we put this illusion at their correct head height, so they look at it dead on, but also it's egocentric based. It's it's percentage of how far they can reach. So that's also pretty important. In this experiment, we did two conditions. We did a monoscopic condition where one eye of the VR headset is blacked out, and they only see through one of their eyes, and do the experiment. And then a stereo where both eyes are open. And then we have three different stimuli. There's the control, which is just the circle. There's a small flanker where there's small flankers around the circle, and large flanker where large flankers around the circle. 5 distances, as I mentioned before, and repeat each one 3 times. Each condition the mono condition was done in one block, and the stereo condition was done in another block, and that alternated depending on subject. You multiply all those together to get 90 total trials. And so let's move on to what we got out of this. And it's actually quite interesting. This is really cool that the large flankers, which appear further away, didn't appear very much further away than the control, only 1.5% further. Now that's interesting. So we were looking for about 5% because each of these are pretty close to being about 5% difference from the control. But we don't see that. And the small flanker one, though, it seems extremely close. We see about double what we expect. Now, there's a few things that might be going on. There's spatial compression in VR that might change things up. Or, we both see and don't see this illusion, so maybe both camps who are arguing might indeed be right, just in very specific scenarios. So was the large flanker condition? Since we're having only cues of relative size going on, maybe it was shown so far out in the distance that it's not in your immediate action space, and maybe something else takes over at that point. We don't really know, and that's really important that we need to attack this problem more and more until we figure out what's going on with this really cool illusion. Going back to the mono and stereo conditions, they actually didn't look very different at all. They're not significantly different through ANOVA, and thanks to that, we're able to pull both groups and get even more information out of our data. So even though the large flanker that looks pretty similar to the control, something's still going on. We still see that there's a response. The response time for each one, for the control and the large, still differ, and the large condition still has the same, like roughly the same time as the small condition. So something's still happening there. The illusion might get somewhat resolved and fixed later, but we don't really know. We might be still crunching away at numbers before we make a decision. Something that's really interesting is when you look at this and you realize in the experiment, each one of these are happening right after each one another. So they should get it's pretty repetitive. 90 trials is kind of a lot. So you're doing this over and over and over, and you should get better and more used to the task. And all of them should kind of blend together pretty well, but there's still this big spike in difference. So something is still going on. And relating that back to the two-stream hypothesis, something is happening with this illusion that a lot of people are very hyped up about, and whether or not it's proof for it or not, I feel like the two-stream hypothesis is pretty agreed upon, but whether or not this illusion is a de facto proof for it is something that's still being debated. A lot of the figures I showed you today are all from the same year, 2001, and all of them come with different results and different findings, and that's kind of interesting. And I think VR is a good way to attack this problem in my personal experience. But when you look at this, right, I'm not saying that their real world experiments is any better than the VR experiments. They have problems, and so do we. It's like comparing apples and oranges. So in VR, you got a brick attached to your face, and that's a little different than real life. And same thing over in real life. There's a lot of things that you can't control for that you can control for in VR. And so even though you're comparing apples and oranges, when you just take a second and zoom out a little bit, you realize that they're both fruit, and they're both are actually attacking the same problem, just in different ways. And that's going to give us what we're all looking for as scientists: it's generalizable knowledge. And that's something really important to me, and really important for a lot of people to look at and just be, well, can we use any of these new tools out here to think differently, think laterally, and understand where we can attack problems in our day-to-day lives? And these different tools that are coming out using technology in interesting and innovative ways. Because if you were to take a lot of problems in your day-to-day lives and just be able to retract, I don't know, whether or not you bump into your sink, it might be pretty helpful. It might not, but in some cases it could be. And there's a lot of applications for this idea. Whether you can see through walls, give yourself flying powers, or whatever you want, there's a lot of that's possible in VR. And giving yourself interesting ways to tackle problems can give us better insight on how to solve further problems in the future. And I just want to go ahead and conclude by showing citing all the papers. I read a lot of papers to get ready for this talk. There's tons of stuff out there about Ebbinghaus. You can go back to that wonderful figure friends show with a whole bunch of cited works about where you can find Ebbinghaus illusion stuff or other illusions. A lot of these other figures I use or the other two figures I use are from that paper, and our paper that I worked with Adam here. But I also want to thank Adam himself and the Hi5 lab for having me on. It's been a great pleasure. And if you have any questions or just want to comment on anything, feel free to email me. I'll try to respond, but I'll definitely read every one of those. And that's it.
Okay, let's see if we can get us both on screen here. Hey, can you unshare your slides for a second?
Yeah.
Okay. Yeah, I think it'll let us do it now. Or maybe it won't. Let's see. It is sometimes crazy figuring out exactly which of these things to hit on Zoom to make us... I want to be on the screen at the same time. Play nice. Let's see, maybe if we get out of full screen mode and do this. Gallery view, there we go. Boom, okay. Okay, Hunter, thank you for your talk. Really cool stuff, really cool.
Okay.
What?
Make sure to check that you're unmuted.
Oh.
You muted both of us, I believe.
I muted us? Okay, are you... Yeah.
I should be good.
Yeah, you're good, I'm good.
All right,
okay. Cool. Okay, so find as many ways as we can to break Zoom. Okay, cool. Thank you, Hunter, for your talk. We really appreciate that. Let's see. So, what if you were to continue something like the work you're working on here? What would your next steps be? What have you got going on, dude?
So if I was going to continue my work on Ebbinghaus, it'd be really interesting to let me formulate my thoughts real quick.
Hey, no problem. Take your time.
The Delboeuf Illusion is actually really interesting to me. It's something that you can actually see, you can experience in your own house right now. If you want to get really up close to a windowsill and pick something in the distance, and then take a step back, focusing on that windowsill, you'll actually have the windowsill converge into your field of vision, making what you're looking at appear bigger. It's really interesting, and whether or not that plays into a major role of these adjusted small and traditional large papers would be pretty cool to test. I did some digging in the most recent paper I found, probably not the most recent, but the most applicable and popular paper I've found comparing these two illusions was back in the 70s. So it didn't give a whole lot of information that I was looking for. It didn't show a whole bunch of what they were doing. So I want to take a fresh look at it and also take multiple attack angles. Like I said, VR is a really cool attack angle that not enough people are taking advantage of. So doing these tests in VR, out of VR, gives a lot more information than what you really expect. I think that'd be a major point to go look at.
So, going back to the Ebbinghaus Illusion and the two pathways, why was what's the relationship there? Why was the illusion used as evidence for the two pathways in the past?
So the Ebbinghaus Illusion, it's able to to fool one side. So
Mm-hmm.
we're not really. Let's just assume we don't know that there's two sides, right?
Okay.
And so what we need to do is figure out some sort of method to show that there's two different sides. There's an action side and a perception side. And so if we can fool one and not the other, well, that's pretty good evidence for showing it. But if you were to find something, let's say some other illusion that either isn't fooled by either, which would be a really crappy illusion, or fools both, that's not necessarily an evidence that there's only there's only one pathway, but it's definitely not helping the two pathway camp. So when you look at the Ebbinghaus illusion and you see that one, even though you know what's behind the curtain, you know the tricks of why, one's appears bigger than the other, but even though they're the same size, but it still tricks you. It still fools your perception. So we fooled one, and now is the other one fooled? And the fact that it wasn't fooled in the first test, the first popular test. Let's see. Let me make sure if I have them. Is it Halfden? But anyway, it's the sorry about that. The gosh, I lost my train of thought just then.
That's okay.
But what fooled one side might not fool the other, and when it doesn't, and it was shown that it didn't, that was pretty cool evidence, and a lot of people took that and tried to replicate it and try and dissect it. And after a few years, there's a few arguments about it and taking it in different ways. So that's what started this whole debacle. But the Ebbinghaus illusion was just a destined illusion to be a good example for it.
All right. Cool. Well, it doesn't look like we have any questions from the audience, but I'm going to go ahead and thank our speaker. In the meantime, if there are any questions, feel free to go ahead and type those. But Hunter, thank you for coming on with us today. It was great seeing you again. Enjoyed the talk, and yeah, it looks like looks like we're set on questions. So in that case, I'm gonna thank our speaker and invite you folks to stay tuned to the channel. We're gonna have a couple more speakers coming up before the summer is out. Next week, I believe we're having Nate Phillips from the AR and VR Perception Lab at Mississippi State. I think it has a new name from when I was there. That's what we called it while I was there. But I think it has a new, cooler name now. Going to be talking about some of his graduate work looking at augmented reality and I believe X-ray vision. So with that said, we're going to wrap up, and thank you all for coming, and thank you, Hunter, for being on with us today, and stay happy, healthy, and safe, folks. Take care.